Now we will see a difference amplifier. Now this is called as a difference amplifier, in which we have applied input to the both the terminals, inverting and non-inverting terminals. This circuit can be solved by applying superposition principle. Superposition principle means this circuit can be analyzed by considering only single source at a time. So applying superposition theorem, first considering only V1. If you consider only V1, then this voltage source V2 will be grounded. If this is grounded, then in this circuit there is no excitation. This circuit will be uh, of no use, so this will be considered as a ground. So when V2 is deactivated, V1 is considered, then this circuit is an inverting amplifier whose output will be V01 will be equal to minus RF upon R1 into Vi. So in the first case we have got the output V0 equal to minus RF upon R1 into Vi. Now this time considering only V2 in the circuit. Second case, considering only V2. When we consider only V2, this circuit is a non-inverting amplifier in which output will be equal to V02, can be calculated as V02 equal to 1 plus RF upon R1. Gain will be 1 plus RF upon R1. In the previous case, gain was minus RF upon R1 into VP. And we know that VP can be calculated from this network as VP, this voltage. According to potential division rule, will be equal to V2 into RF upon R1 plus RF. This will be substituted here. So this voltage will be equal to 1 plus RF upon R1 into RF upon R1 plus RF into V2. Now cross multiplying, we get R1 plus RF upon R1 into RF upon R1 plus RF into V2. This will be cancelled out, will be equal to RF upon R1 into V2. And we know that this is the voltage V02, and we know that V01 equal to minus RF upon R1 into V1. So the total output will be equal to V01 plus V02 will be equal to RF upon R1 into V2 minus RF upon R1 into V1. This will be RF upon R1 into V2 minus V1. So this is a difference amplifier. Now we will solve one question from gate exam. For the op amp circuit, calculate V0. We have to calculate this voltage V0, and the circuit is given as. Now this circuit can be simplified as this 1 volt source will be at both the input terminals. Now we know that this is like a difference amplifier in which there will be two output V01 and V02. So this V0 will be equal to V01 plus V02. We know that V01 will be output due to this 1 volt and V02 will be output due to this 1 volt. So V01 will be a output of inverting amplifier, which will be equal to minus 2 kilo ohm, which is RF, divided by 1 kilo ohm, which is R1, into 1 volt, which is applied input, plus with V02 output is output of non-inverting amplifier. For this non-inverting amplifier, gain is equal to 1 plus 2 kilo ohm divided by 1 kilo ohm. The 2 kilo ohm is this resistance, 1 kilo ohm is this resistance, minus 1 plus RF1 R1, this is the gain, multiply this voltage Vp, which can be calculated as 1 volt, applied 1 volt, multiply this 1 kilo ohm, divide by addition of both the impedances, 1 kilo ohm plus 1 kilo ohm. So this will come out to be minus 2 volt plus 3 into 1 by 2. So it will be equal to minus 2 plus 3 by 2 equal to minus 1 by 2 volts, equal to minus 0.5 volts. Now the next topic will be an integrator. Op amp can be used to design an integrator, as in this circuit there will be slight modification. A capacitor is used in place of RF. This circuit has output V0, which can be solved in two different by solving can be solved by using two different types of calculation. First, in S domain, we know that there is a capacitance whose operation depends on frequency, means S term will be there. So uh, the conversion of R1 in S domain will be itself R1. Conversion of C in S domain will be equal to 1 by CS. So we can say that see that this circuit is an inverting amplifier whose output can be directly written as, sorry, this is VI, can be written as V0 equal to minus RF upon R1. Note that this is impedance and this is not an impedance. Its impedance will be 1 by CS. So V0 will be equal to minus 1 by CS upon R1 will be equal to minus 1 upon R CS into Vi. Sorry, this will be multiplied with Vi. So this will be minus 1 by R into C, and we know that S in denominator will be replaced by an integration in time domain will be equal to Vi into dt. So as output V naught is dependent on integration of Vi, this circuit is an integrator. Now we will solve this circuit expression of output of this circuit in time domain also. Consider the same circuit. Now we know that Vp equal to 0 volt, this potential Vp equal to 0 volt, so this potential Vn will be equal to 0 volt according to virtual current concept. Now at this point we will apply KCL. This will be one current I1 and this will be one current IF. So applying KCL at Vn, if we apply KCL at Vn, we'll get total incoming current should be equal to total outgoing current. So we have both outgoing current should be equal to 0. Now I1 can be substituted as Vn minus Vi, seeing the direction, divided by R1 plus IF. Note that this current IF is a current of capacitor, and before writing the equation for capacitor current we will give the polarity to the capacitor voltage across capacitor. As current is moving in this direction, current is flowing in this direction, we will have potential as Vc. If direction is this, then polarity would be this. So a capacitor which has a current in this direction would have polarity of voltage in this way. So the current equation current is written as I equal to C into dVc by dt. The same equation will be used here. So we get IF equal to C into dVc by dt equal to 0. And from the circuit we know that Vc equal to Vn minus V naught will be equal to minus V naught because Vn is equal to 0. So this equation can be reduced as minus Vi upon R1 plus C into d by dt of minus V naught will be equal to 0. Now solving this expression, minus Vi upon R1 minus C into d by dt of V naught will be equal to 0. So d by dt of V naught will be equal to minus Vi by R1 divided by C. So d by dt, taking integration on both sides, therefore V naught equal to minus 1 upon R1 C into Vi into dt. This is the expression for output in time domain. So the whole expression was in time domain. Previously we saw it in S domain. Now differentiator. Differentiator circuit will be uh, same like an integrator. uh, R and C are interchanged. In this circuit, S domain conversion of RF will be RF. S domain conversion of C will be equal to 1 by CS. So Looking at this circuit, we know that this is an inverting amplifier. This voltage Vp and this voltage Vn. For this inverting amplifier, we know that its output expression is minus Rf upon R1 into Vi, and R1 voltage for this, for R1 resistance impedance for this circuit is equal to 1 by Cs. So for this circuit, V0 will be written as minus Rf upon 1 by Cs into Vi will be written as minus Rf into Cs into Vi will be written as minus Rf into C, and we know that S in denominator can be replaced by d by dt of Vi. So V0 is equal to minus Rf into C into d by dt of Vi. So this, in this circuit, the output depends on differentiation of input, hence it is a differentiator. Now we will solve one gate question. For the circuit, shown in the figure, C is initially uncharged, full stop. At t equal to 0, switch S is closed, full stop. The voltage Vc across the capacitor at t equal to 1 millisecond is, the circuit is the options are 0 volt, 6.3 volt, 9.45 volt, 10 volts. Now in this circuit, don't mug up the output equation. It now, when switch is closed, we will start analyzing this circuit. At this point, voltage Vp is clearly seen 10 volts, so this voltage Vn will be equal to 10 volts. At this point, we will have two currents, I1 and this IF. So applying KCL at Vn, when we apply KCL at Vn, both the outgoing currents I1 IF will be equal to 0. So substituting for I1 and IF, we get Vn minus 0 divided by 1 kilo ohm plus Vn minus V0. Sorry, this is a capacitor current, which is written as C into d by dt of minus Vc. Minus Vc is taken because the polarity across capacitor is not according to the direction of current, it is in the opposite direction of current, so I have taken uh, to compensate this as minus Vc equal to 0. Now we know that Vc is equal to V0 minus Vn. So substituting, we get Vn upon 1 kilo ohm plus C into d by dt of minus V0 by Vn, so it can be written as Vn minus V0 equal to 0. So sorry, in this problem we want to calculate only VC, value of VC, so no need to substitute this. So uh, this step can be written as VC and this sign will be negative. We want to calculate only VC, not V naught, so no need to substitute. So this can be reduced as C into d by dt of Vc will be equal to Vn upon 1 kilo ohms, will be equal to Vn is 10 volts divided by 1 kilo ohm. Now dVc by dt will be equal to 10 volts divided by 1 kilo ohm into this C will be 1 microfarad, 1 into 10 raised to power minus 6. So solving this we get 10 kilo ohms or 10 volts divided by this will be 10 raised to power minus 3. Now we know that initially the capacitor voltage was 0 volts at t equal to 0. Now we have to calculate Vc2 at t equal to 1 millisecond. So we know that dt is equal to 1 millisecond and we want to calculate dvc, which is equal to vc2 minus vc will be equal to vc2. So we will get this value. So dvc by dt is 10 volt by 10 raised to power minus 3. From this we get dvc equal to 10 into 10 raised to power minus 3 into dt will be equal to 10 by 10 raised to power minus 3, and dt is 1 millisecond into 1 into 10 raised to power minus 3. This will cancel. So we know that dvc is equal to 10 volts. dvc will be equal to vc2 minus vc will be equal to 10 volts, and we know that vc was 0 at t equal to 0, so vc2 will be equal to 10 volts. So at 1 millisecond capacitor will charge up to